Yeah, thank you. So I'm Ruven Pillay. So I work at the IIIF, and I'm also a maintainer of the IIP-image IIIF server. So my talk is going to be looking at server performance, IIIF server performance, looking at the various factors and doing some benchmarks and showing you quantitatively what impact these factors have on performance. So why is performance important? Well, of course, user experience, response time is a key element here. There's an implication for cost if your server is not efficient. You're going to need extra compute infrastructure. And there's even an environmental kind of case. The more compute use you use, the more energy you use. So the goals of this talk are to look at some of the key critical factors, quantify how these impact performance, and we're going to focus on the most common IIIF use case, and the thing which is most sensitive to performance, so pan and zoom kind of use. Of course, there are other uses for IIIF, but we're going to focus just on this. And at the end, I'm going to look at how we can improve performance even more through hardware acceleration. So I'm going to look first briefly at issues around infrastructure, your runtime environment, image formats, in terms of input formats, how you encode your images, the output formats you choose, and the transcoding step. And then I'm going to benchmark various different IIIF servers. And finally, yeah, look at the issue of hardware acceleration. So infrastructure, I'm not going to talk too much about this, but the key element for a IIIF server is access to the images. So it's disk speed. Your IIIF image server is very sensitive to disk input-output, which means that I know a lot of people use S3, but this is very slow, and it's not really suited to fast random access. Of course, there may be other reasons to use that. Caching, various IIIF servers have their own sets of cache, and there are also web server higher level caches that you can use to speed up, to effectively avoid having to query the server. So these are more generic kind of issues. I'm going to focus more on things that are more relevant to, or more focused on IIIF. So runtime environments, nowadays a lot of people use virtualization, so things like Linux containers, Docker, even sometimes VirtualBox. So Docker is the most widely used container environment. So we know virtualization is going to entail some sort of performance hit, but let's see how much of a performance hit is there. So I did some tests using pan and zoom tile requests to IIP image, using just the default parameters, and compare a bare metal, pure compiled version to the official Docker image. And you expect there to be a kind of performance hit. So this kind of quantifies just how much. So there is a 60% penalty to using Docker. So Docker has its uses, it's very practical, but you should be aware there is a non-negligible performance hit. And I think it's really due to the disk, to the reading from Docker into the file system. Image input format. So ideally, so your choice of input format can have a big impact on server performance. So the most widely used formats are things like TIFF, JPEG 2000, even JPEG. So the ideal format would need to handle the most common types of images, and handle various bit depths, resolutions, metadata. It has to be scalable, and it should handle efficiently random access, so access to regions or tiles without having to decode the whole image. But how an image is encoded, so beyond your choice of format, how you encode and structure the image can actually make quite a big difference on decoding side. So let's take a first look at JPEG 2000, which is a widely used format in the IIIF community. It's a flexible format, has excellent compression. There was a recent extension called HTJ2K, and how you encode your JPEG and how you structure it can make a big difference. So JPEG 2000 has features such as precincts, code blocks markers. We did some tests and presentations on this a couple of years back. For more details, you should have a look at these presentations we did at previous IIIF conferences and this publication on in the Code for Lib journal. So I'm just going to recap just one or two conclusions from those studies. In terms of encoding parameters, so this is interesting. So look, on the left here, we have a default encoding using Kakadu with no precincts, no tiles, no markers. And here we're comparing the decode speed to if you start to introduce precincts here, precincts, if you introduce markers, if you use HTJ2K, the extension. So as you can see, if you start to use precincts and nothing else, you get a 12% improvement in decoding speed. HTJ2K gives you an even better speed improvement. And if you look at the end, if you combine all the different optimizations, you can get quite a big reduction in decoding speed. So you see right on the right here, you have a quite significant improvement in speed. In terms of decoding, this is highly dependent, of course, on your choice of codec. So there's OpenJPEG, Kakadu, and we can see there's a big difference in the performance of OpenJPEG compared to Kakadu. So there's a difference of a factor of 10 almost between OpenJPEG and Kakadu. This is on the left for lossy and lossless decoding on the right. And I've normalized all these to, the scale on the left is normalized to the speed of tile pyramid TIFF. So even with Kakadu HTJ2K, it's still a factor of 3 or 4 times slower than TIFF. So just to understand the scale here, so even the best optimization is slower than TIFF. So JPEG has obviously better compression characteristics than TIFF. HTJ2K is definitely faster to encode and decode, so it's definitely an option you should be thinking of. OpenJPEG, unfortunately, is very slow at the moment. And your choice of parameter, encoding parameters, makes a big difference. So in our paper, which we published, we suggested some optimal encoding parameters. So here's an example here. So you make sure you use code blocks, make sure you use your precincts, and use the appropriate markers. But as I said, yeah, TIFF is actually, for pan and zoom use at least, TIFF is actually faster. So let's have a closer look at TIFF. So just as with JPEG 2000, it's a format which is widely used, very flexible. It handles various types of compression, lossy, lossless, and there are options you can encode using JPEG, WebP, LZW, deflate, etc. It has support for multiple bit depths, so it's even more flexible than JPEG 2000 for that, and it has strong metadata support. So how you encode your TIFF, just as with JPEG 2000, makes a difference to the decoding speed. So let's look at, so you want tiles, sorry. You want to include tiles, a pyramid resolution, so this is tile pyramid TIFF. So what difference does that make compared to normal, standard TIFF, strip-based TIFF? So here's a test I did with Cantaloupe, tested on an untiled TIFF versus a tiled pyramid TIFF. And you can see there's a big difference here. So again, these values are normalized. The fastest one is normalized to 1. And you can see it's 250% slower to use normal TIFF. So just how you encode your TIFF makes a big difference. In terms of compression, so obviously if you don't compress, so TIFF, you can still use your pyramid TIFF, but not compress. So pyramid TIFF without any compression, that's the one on the right on the left, is obviously going to be the fastest way to use it, but your file is going to be much bigger. So let's look at lossless encoding. So you have different types of compression supported by libtiff, so LZW, deflate. You can also even use WebP nowadays. Z standard is quite a fast compression format, which was recently, in the last few years, added to libtiff. So it's not going to be supported in commercial software, but it is standard in the open source libtiff. In terms of lossy decoding, there's JPEG and WebP options. in terms of speed, obviously uncompressed, tiled, multi-resolution primitive is by far the fastest. But as we saw, lossless compression, I go back here, Z standard actually beats deflate or LZW by quite a margin. So this is if you're using, if you want lossless compression, this is a good option. Lossy WebP, go back here on the right here, it has comparable, it's a bit slower, but it's comparable performance to JPEG, and yet it has much better image quality for the same size of image. I actually did a kind of a lightning talk on one of the online meetings, so there's more details if you want to go into that further in the 2024 online meeting YouTube channel. So finally, I'm just going to look at JPEG. So JPEG is not optimal for streaming. It's widely used, so a lot of people have to use this, but it lacks the multi-resolution structure. So let's have a look at how this compares. So again, so it doesn't have the multi-resolution structure. So here we're showing how a IIIF server decodes each resolution, virtual resolution level from a JPEG. So JPEG does have this notion of DCT cosine blocks within it. So you can do some relatively efficient resizing. So here, as we go down the resolution levels, we can see it gets slower and slower. And the scale here is normalized to the equivalent image in the exact same image, but in TIFF format. So a JPEG is like 300 times slower than using an uncompressed pyramid TIFF. So just to give you a kind of idea of the scale of difference that we're talking about. So that's the image input formats. But when you're using a IIIF server, often you're transcoding into a different format. So your input image is in JPEG 2000 or TIFF or something else, and you're requesting something back in JPEG, often. So this step, so typically you're outputting a format which is native to web browsers. So typically JPEG, WebP, PNG, and also nowadays you have modern web-compatible, well, browser-compatible formats such as AVIF, JPEG XL. So this transcoding step is quite a heavy step. You have to decode the image. If there's any image processing to do, such as resizing or something else, you have to do that. And then you have to convert it back into another format. So let's kind of test how long this takes. So we're going to use an uncompressed tiled primitive as our input, just so that we don't have any effects from the compression there. And we're going to measure this using, here I'm using just IIP image to do the benchmark here. So this is the transcoding speed. So it's normalized to 1 for the fastest. So JPEG is very fast. JPEG is using libJPEG Turbo, which is highly optimized. Deflate is actually surprisingly reasonably fast. But as we go down, so WebP is about 8 times slower. And as we get into these more recent formats such as AVIF and JPEG XL, we're hitting like 40 times slower than the standard JPEG. If we look at the size, so the speed, what's important is not just the speed, because you have to send this image back to your user. So size has an impact as well. So let's have a look here. So obviously, something encoded in deflate, lossless deflate, is going to be much, much larger. WebP is a more efficient format, so it's actually a little bit smaller. So you can have, even if it's slower to encode, it may well be useful to use that. PNG, of course, is lossless, so it's much slower. And what was surprising here on the right, so AVIF and JPEG XL for very small tiles, so the kind of tiles you get in a pan and zoom viewer. So these are modern formats which are supposed to compress better than JPEG, and they do. When you're using a large image, they actually do it quite well. But when you scale down to very small images, there's a lot of overhead, and actually they end up a little bit larger than JPEG. So JPEG Turbo remains the fastest encoder for transcoding. But WebP is a reasonable alternative. And yeah, as I said, these newer formats have promise. These are going to be optimized further as they develop, but they're not ready yet. So how can we accelerate this transcoding process? So, of course, if you're doing rotation or resizing or changing contrast or something like this, then you have to go through this process. But in pan and zoom use, often you're not doing anything to the image. You're just giving the tiles back as they are. So how can we accelerate this process? Well, we can just avoid it. Why don't we just skip that process? So in the last version of IIP image, we introduced this low latency pass-through mode where you bypass this encoding step, this decoding encoding step. That obviously only works if your tiles are perfectly aligned to the structure within the TIFF. It only works for TIFF. And it only makes sense if you're using a compression format which your browser can read anyway, such as JPEG or WebP. So what impact does that actually make? So if we just look at the pure transcoding step, then the speed is going to be very fast. You're reducing that step almost to zero. But if we look at the whole chain, because when you're using a IIIF server, it's not just processing the image. You have to deal with the request. There's a lot of extra overhead in terms of latency for sending the image, getting it back. So if we look at the real world impact, yeah, for JPEG, we get like a 25% performance improvement. These are all times, so the lower the better. We get an improvement there, but libJPEG Turbo is actually very efficient. So we're not seeing a huge difference for JPEG. However, for WebP, as WebP is relatively slow to encode, this starts to make a big difference. So it's about, yeah, we can see a much bigger difference, like a 30% difference, yeah. So let's put all this together. I'm going to benchmark various different IIIF servers to see how they compare for different types of images and different scenarios. So I looked at here 5 different servers. There are other IIIF servers that exist, but some of these are quite difficult to get running. So I looked at Digilib, Cantaloupe are both Java-based. There's one called Race, which is written in Go. And there are 2 C++ ones, which Sippy and IIP image. So I used the latest version for each of them. And we tried using various input formats. Some of them don't support all of these input formats, or some of them have problems with some of these formats, but try to use the common input formats. So we used an identical set of images of paintings for each of these servers, identical IIIF requests, fixed the JPEG output quality level to the same, and we're not doing load testing or concurrency here. It's just pure speed of the process, right? And we're using all this on bare metal. So I said Docker has some overhead, so the idea was to avoid any impact from Docker on the test. So these are all compiled onto Ubuntu and run locally on localhost. So we avoid also network effects. So let's have a look. So this is if you have a TIFF, tiled pyramid TIFF as your source image. You have various servers, and you see there's actually a big difference. So what was surprising here was Sippy on the right is written in C++, so you would imagine it would be quite fast, but actually I was surprised at how slow for TIFF it was. It's about 8 times slower than the fastest here. Cantaloupe performs quite well. And other servers such as Race, they don't actually support TIFF. So, and as we can see here, I mentioned this low latency pass-through mode. So the third one here is actually the fastest because it's avoiding this transcoding step. So these are for TIFF, both TIFF JPEG and TIFF uncompressed. In terms of JPEG 2000, the performance is a bit more equal. So Cantaloupe performs pretty well, and in this case, Sippy actually performs really well for JPEG 2000. So here I've tried with JPEG 2000, classic JPEG 2000, as well as HT-JTK. And so you can, as you can see, HT-JTK for every server improves performance. Sippy actually couldn't handle HT-JTK files for some reason. But as you can see, the performances are all pretty good for JPEG 2000. And what about JPEG? So if you're running on a JPEG, well, we said earlier that JPEG is not an ideal format for pan and zoom streaming, but sometimes you have to use that. So let's have a look. And here we can see there's actually a very big difference between servers again. So CP, as with TIFF, is extremely slow. It's over 12 times slower than the fastest one. Whereas, Cantaloupe, it's a bit slower, but it's reasonable, 4 times slower. And Digilib performs 6 times slower, reasonably okay. So, performance is highly variable between servers. We found IIP, I'm the maintainer of IIP image, so you should do. So I'm obviously not biased at all, but obviously it is the fastest. You should test this yourself. So we were looking really at performance. So there are other important criteria that we didn't test, but maybe should be tested at some point. So stress testing, how do these perform under load? How robust are they? In these tests, some of them did produce errors on certain images. So how reliable, robust are these servers? How much memory use? So if an image, for very large images, some of these servers have problems. So Digilib, for example, had issues with images beyond a certain size. So scalability, loads. And then I was looking at pan and zoom. So there are other use cases for IIIF when you're just resizing an image, this kind of thing. So this is a kind of different criteria. So I'm going to finish looking a bit at hardware acceleration. So how can we go even further and improve? So we can see that there are optimizations to make in terms of input image, output image, the whole transcoding step. Can we actually go even further? So, we can use hardware acceleration. So obviously, the drawback is it's hardware dependent. As you switch to a different machine, it's not going to work in the same way. So often you have manufacturer-supplied libraries, which are sometimes proprietary and only partially open source. So sometimes it's not ideal, but there are various technologies. So there's on the CPU side using SIMD, so things like Intel's One API. There's ROCm from AMD. Highway is open source. And on the GPU side, there's CUDA from NVIDIA. So I did some tests using CPU acceleration. I've integrated this into IIP image to do these tests. So using Intel's One API, they have a sub-library called the Integrated Performance Primitives, which provide a set of optimized image processing routines. So it uses SIMD and allows you to exploit the features on your processor, SoC, AVX, this kind of stuff. It's made by Intel, so it only works on Intel chips. So I did some tests to measure the kind of gain in speed you get, not from the transcoding step, but from the image processing step. So imagine you're doing some sort of resizing or rotation or something. So I tried this both on a laptop and on a real server to see if that made a difference. So here's the difference it makes for bilinear interpolation. So when you're resizing an image using bilinear interpolation, so on the left, that's just on my laptop, and on the right is using a high-end dual Xeon 24-core server. And the blue bars are unaccelerated, so it's the normal implementation, and then you have the hardware-accelerated implementation. So I'm just timing this processing step, and you can see the huge gain in speed. So this is something which is quite promising for this kind of processing. And even on the right, you can see how it scales with the number of processors. So these libraries are actually quite well written. I noticed an anomaly here. It goes back up. This server has 2 CPUs, each one with 12 cores, and I think there's some issue as it reaches the 12 limit, switching between processors and stuff. So finally, I'm going to look at CUDA. So what about GPU? So previously, it was rare to have a GPU on a server, but because of AI, we're now starting to see servers which have GPUs. So if they're there, we may as well use them. So NVIDIA have released things like NV JPEG 2000, which is a JPEG 2000 codec, which uses hardware acceleration to speed it up. It doesn't support every type of JPEG, so it's a bit more limited than Kakadu, but it supports the main kind of subset of JPEG 2000 images. So, I don't have numbers for this, but in initial tests, you'll have to wait until next year for that. But in initial tests, the performance is actually very competitive to Kakadu. So it is an alternative. Well, so Kakadu. Well, I thank them for the reception yesterday, but you can avoid. Sorry, don't tell them. You can avoid paying your Kakadu license fee by buying an NVIDIA graphics card, which lasts for years and years. So this is a potential option. Sorry, if anyone from Kakadu said, sorry, I didn't say that. So conclusion is server performance, yeah, it really depends on a number of factors. The suboptimal choice of image format can result in significant penalties in terms of performance. Choice of input format, how you encode that image, what format you choose to output. Things like virtualization are very practical through Docker, but you have to know it does entail some overhead. And your choice of IIIF server has also an important impact on performance. It can be actually highly variable, and it depends on the type of image you're using, whether that server is optimized for those type of images. And yeah, benchmarking I think is something useful for the community and for developers. We have a talk just after on a similar theme. Hopefully, it won't completely contradict everything I've said. So yeah, just to finish, the next release of IIP Image, maybe towards the end of the year, we're going to have JPEG XL output support, multiple bit depth support, so up to 10, 12, 16-bit output, which also means you have high dynamic range support. So, and some of these hardware acceleration features will hopefully feature in this next release. So, thank you.
Hi, good afternoon. I'm Matthew from the University of Chicago. And in my presentation, I'll be giving my version of benchmarks for image servers and file format performance. So first, what was the motivation for this test? So the university library that I work for is it's building a new collections platform called UChicago Node, and it's going to be powered by IIIF. And one of the things that we wanted to do was to take advantage of API, Image API 3, but current infrastructure only exclusively supports Image API 2, so we obviously had to look for a new server. And to really inform our decision, we looked at 4 main categories: storage, speed, quality, and operational fit. So what did we exactly evaluate? So we picked 3 servers, very popular, widely deployed. So the first is Cantaloupe, and then IIP-serve, and Triplet. So Cantaloupe written in Java, IIP-serve C++, and Triplet in Go. And to test the servers, we sampled 10 images from the collection, books, maps, scrolls. And the 10 images varied in spec, so we can see, they have different megapixel count. Some of them were small, medium, large by categorized by megapixels, and they all had different bit depth. Notably, only one was 16-bit, which we'll see produce quite interesting results. And to test file format, I tested purely based using pyramidal TIFFs, not uncompressed and with LZW compression. And so I now speak about the methodology of doing these tests, which can be categorized in 3 parts: storage, speed, and tile quality. So to answer the storage question, I first made 2 sets of files, so with no compression and with compression using VIPs. And now I'll talk about the speed test. And so for all 3 servers, they were all deployed with Docker, and some of the settings had to be tuned to ensure a more balanced and fair test. So one of these settings were like the JPEG quality, so they were set to 75. And for each server, 5 kinds of requests were made. And for each server, an image and format combination. And so the first request that was tested is the info.json request. So it's grabbing the info.json data, which is purely metadata about the image, so no pixel processing. And the second request is getting a thumbnail. And the third request is getting a mid-zoom tile. And the fourth request is getting a high zoom tile. And the fifth request was the most expensive. So it's a combination of the previous 4 requests done in sequence. And so to time the requests, I just use curl without getting like the body response. So just simply getting HTTP response, the time for the first byte, total time taken, and total bytes downloaded. And of course, I also tested caching conditions, so testing the request with cold cache, warm cache, and with concurrency. And this is like the full, breakdown of the test. So starting the Docker containers, getting the CSV headers running, and testing with cold cache, warm cache, and concurrency, and then cleanup. And now I'll speak about how the testing of the tile quality was done. And so to test the tile quality, it's a comparison between the JPEG tile with lossless reference from using the source images. So generating a lossless thumbnail with VIPs, and then getting equivalent from each server JPEG thumbnail, and then making a comparison using 2 metrics, which is the structural similarity index, which simply compares 2 images using in 3 dimensions, luminance, contrast, and structure. And then using the metric signal to noise ratio, which simply measures a pixel fidelity between 2 images. And both metrics were used, computed using a scikit image, which is a Python library. And so before talking about the findings, I have to be very frank about the limitations. So the first one is that I ran all of these on all the tests on my MacBook. So yeah, it's the numbers can't be generalized in a real production environment. And the second limitation is that, we're just using the collection of UChicago to run these tests, so the numbers might be very different with entirely different collection. And the other limitation that I note is, I'm just running a very, very small sample of 10 images and of a very limited type. And most of these images are 8-bit, so not like crazy big. And also these tests are just using very limited tile coverage, so it's not super extensive. I think, and the last part, I think the major limitation is that I have like really limited knowledge on image server architecture and benchmarking. So yeah, I think we have to take that into account as well. So let's speak about findings for storage. So unsurprisingly, LCW compression yields some savings in storage. And what was interesting to me was that for the 16-bit image, there was actually not much savings when it came to compression. So I think we only saved, I think, about 9 megabytes with the 16-bit image, which was very surprising to me. And so now let's talk about speed. And so one thing that stood out was having primitive with compression and no compression really did not have a lot of effect on speed when it came to making requests in a warm cache environment. So yeah, we can see that the differences are pretty marginal in the last column. So yeah, we're talking about fractions in time. And what was, I think, more interesting to me was that some servers were pretty sluggish when it came to like making requests in cold conditions, especially for like the 16-bit image. So we can see here with Cantaloupe, it was really struggling with getting the cold thumbnail at 78 milliseconds, and but that significantly improved in warmer conditions with 2.8, and yeah, that is like the most like staggering difference as we can see here. But in general, all three servers are very quick. I think looking at this stat, one thing that stood out to me was I think was triplet. Somehow it performed better cold than warm, as we can see in the high zoom cold to warm ratio. So I think there may be something weird about my method. So I think I have to really look into that. But yeah, that was pretty fishy to me. So now I'll now talk about the concurrency findings, and I think broadly I didn't find any like major like drop in performance when it came to like making 5 or 10 simultaneous requests on these servers. So if we look here, in the columns in green, the servers perform pretty they're pretty stable in both scenarios, making 5 simultaneous requests and 10 for majority of the results at the 50th percentile. And in terms of tile quality, I can say that IIP-serve produced the most faithful JPEG tiles, followed by Cantaloupe and followed by triplet and then Cantaloupe. And as we can see here, what does it say? There is really no difference whether you feed uncompressed primitive or compressed primitive in terms of the EO you get at the output, but really the difference is the choice of the server and its resizing algorithm. So let's wrap up with takeaways. So for UChicago, ultimately, I think we're very convinced that all 3 servers were like very, very quick. And the deciding factor was actually our infrastructure. So we run like our servers with free BSD. And from what I know, IIP-serve was the only server that had a free BSD port. So that option meant that deployment will be much, much easier. So we simply went with that. And in conclusion, I think the first point maybe is I'd like to emphasize on is that it seems from this study that file format compression is largely a storage decision. And second, the choice of your image server will influence the output of your JPEG tiles in terms of fidelity. And I think the underscoring point is, all of these servers are very quick, and I think the test that I would like to take on next is to really test these servers with much larger images, especially images that are 16-bit. So I think that was the key limitation that I found quite late in my test. So really to conclude, I think I tried to be as thorough as possible with this test, and I think clearly there are a lot of refinements that can be made given some of these, some of the odd results that I got. So I'm really happy to take any ideas and feedback on improving these tests. Thanks.
Hello, everybody. As a heads up, we will not be benchmarking anything in this presentation. So sorry if you're hoping for a three-peat there. My name is Dan Brennan. I'm joined by my colleagues Elena Mujal and Sebastian Siclait. We are all developers with Getty Digital. A bit of context for that, we represent two different developer teams. Elena is with the APIs, infrastructure, and data team, so our back-end ETL processes that transform, model, publish data. Sebastian and I are with the research applications team. We consume that data and make beautiful interfaces that people can interact and play with and look at. Today we are going to do sort of a show and tell how it's made presentation. Getty has rich collections. We are a museum, we are a library, we're an archive. As such, we have many disparate source systems for managing those data and managing that data, all of the resources associated with it. So we're going to talk about sort of how many different processes and many different pipelines sort of merge with the presentation APIs of Vertex so that Sebastian and I are somewhat blissfully unaware of the work that Elena and her team do to publish all of that data. That said, I will turn this over to Elena, who will kick us off. We'll kind of go back to front here.
Yes, so hello. Today I just want to start by mentioning some of the mini systems and tools that we use to build out our transform pipelines and workflows. This is just kind of a fraction of them, and you may or may not be familiar, but thought I'd mention them in case I mention them later, and they might make more sense then. So first we use Gamma, which is the Getty Asset and Media Management application, which is our DAM system to store, catalog, access, manage Getty digital resources, so image, audio, PDFs, all kinds of things. And kind of something that's important here is that the data is at the image level or at the kind of individual resource level. It's also integrated with IIIF Image API, so we have a published IIIF URL that's included for most of those assets if there's a IIIF image available. TMS is the collection management system that we use. That's for all museum and trust assets. There's also some research assets that are included in there, and item level metadata is recorded there. Rosetta is our digital management and preservation system used with archival collections. And something that is kind of different there is that the metadata is typically documented at the IE or intellectual entity level. So these are kind of in larger formats, not at the item or at the image, but more kind of conceptual collections, things like that. And then Arches does a similar job where we use it with archival collections for digital preservation and for asset management. And then item level metadata is recorded. And like Dan mentioned, since we have so many different source systems, a lot of these workflows are kind of created based on how can we use the different levels of metadata in different places and use that when we're creating our linked art, JSON LD, and our IIIF manifests. Some internal tools that are really useful and really help drive this process are GCIS, which is our image service, which is a suite of ETL tools to convert our media files and metadata into IIIF images. We use IIP server, thank you. And then we originally used this same tool to create the manifests, but as part of this recent update in our workflows related to the presentation API, we actually moved outside of GCIS and into task management. And so task management is a set of services deployed on a Kubernetes cluster. And we use Celery to queue asynchronous tasks, Celery Beat to schedule them. And so part of this process was trying to analyze how can we best have kind of as much hands-on experience with the manifest process if there's any kind of intervention that's needed, and then also taking advantage of parallel processing wherever we can because we have some really, really large objects and also a lot of things to get through. ID Manager is also something we use, which we can use to query links between identifiers in the Getty holdings. So if you have a local URI, you can find all the things that it's connected to and if they exist. And then we also have LOD gateways, which we have one for the museum, for the research collections. We have one to hold annotations, which includes things like transcripts. We also have it for visual items and other media-related assets. So it's a document store with a graph expansion and graph storage, and so we really take advantage of that and use quite a lot of Sparkle queries when working on our manifests. So first I'll start with kind of what I think of as being the most unified process thus far and kind of has some of the less messy bits and has been standing for the longest. And so images are deposited into Gamma, and then item level metadata is deposited into TMS. Images are also deposited into TMS, and then that data goes through a transform process that's part of our existing linked art infrastructure. So before building out the manifest, we are building out the human-made objects, the visual items, and that's really what fuels the manifest creation process, going through that transform, being able to kind of identify, are there visual items? Yes, then we need to create a manifest and getting all of the relevant metadata that we need without having to go and interface with TMS or the level 1 JSON, which is just a exact replication of the data in TMS, but at the JSON level, it kind of has already been drilled down to just kind of the core fields that we want. So for that manifest creation process, a manifest ID is searched for through the ID manager. And if it exists, we want to use the same ID. And if it's not, then we create a new one using slugs and add that to the ID management so that we can continue to track those connections. We then do a federated Sparkle query through the HMO and all of the visual items as well to kind of get more of that detailed information, rights information, item metadata, descriptions, things like that. And we've built out new version 2 and version 3 processes and updated those. This was one of the big moves from GCIS to task management because this process was already fully built out in GCIS for the version 2. And kind of for all of these, creation of version 3 was a real motivator and kind of taking another look at the processes and updating them, creating new ones. And then all of those manifests are then uploaded to the GCIS database to be served. Next. So another workflow that we have is pretty collection specific, and so this is the Edward Rouchet collection. It was kind of a pilot project that was done that I think really demonstrated the power of having item level metadata and how that could be used in the research collections viewer. And so it is kind of a one-off in the system in the way that it was brought in and uploaded into our various source systems. And so images and metadata originally deposited into Rosetta as part of an IE, as many of our archival collections were. And then the workflow was created to migrate image level data into Gamma and item level data into Arches. And this is similar to the next process, and we are waiting on this because we already have item level data available in RCV, so it's not a priority to migrate that collection first. And then for that, the manifest creation process uses Arches and Gamma. For that, I'm realizing I think my slide's incorrect, but we use Rosetta data, IE data, that we then parse and then bring that in. And that's kind of something unique about this process is that it really depends on metadata at a higher level than the other two workflows because that's what we currently have available. And for that, only a new V3 process was built out, and that's because we'll eventually put it through the next workflow, which is called the dam consolidation workflow, where we migrate. But as of now, the V2 are pretty much standard, and they're going to stay the same, and we focused on kind of making sure that the version 3 provided the same metadata and were up to date in the spec. And then those manifests are also uploaded to the GCIS database. This is kind of the last workflow that I'll talk about, and kind of the newest one that we've been working on. It's called the dam consolidation workflow. And so this was really, it had multiple motivations, one of them being that we wanted to take data that's currently in a digital preservation system, which is Rosetta, and is meant kind of for archival purposes, and move it into our current system that's better focused on digital asset management. So all of the data will still remain in Rosetta for preservation purposes, but we want to move it into Gamma and Arches so that we're able to kind of have item-level metadata and also kind of separate those systems and use them as they're intended. So originally, this data was deposited into Rosetta as part of an IE, and we've created a workflow to migrate the image-level data into Gamma and the item-level data into Arches. This has taken a lot of collaboration with the team at the GRI, because we need them to help us kind of determine those item-level groupings. Right now, that is a manual process. We've developed some slightly automatic processes as well, where it's possible, where we know there are things like a recto verso, and that's very consistent throughout the whole collection. But it has really been kind of a team effort there of figuring out how we're going to split things, assign ref IDs, and things like that. And so because we do all that work at the front end before we upload to Gamma and Arches at the image and item level, it makes the manifest creation process really quite simple, just using that data that we inputted into Arches and Gamma. And then we built out both version 2 and version 3 processes for that. And then those manifests are actually uploaded to media LOD. And so we're kind of moving things around and seeing where things can best be placed and best be used. And slugs are another thing that are used in this collection and are being kind of moved over and used for museum items as well, and new developments. So some quick challenges that we've encountered is complex objects and chicken and egg relationships. I think we're very lucky in a way that we have such well-structured linked art infrastructure. And so those Sparkle queries have been extremely useful in kind of determining what levels to drill down to, how to organize that data, and determining which parts to actually include without having to go through and fully parse everything. It also was part of our motivation to move the process into task management and out of GCIS, because GCIS handles our images and it used to handle manifests. What would happen is that occasionally, if a lot of work was being done, if we're updating lots of images and also some very large manifests with thousands of canvases, workers would time out. We would kind of run into issues here and there. And so we wanted to kind of stop it from interrupting any kind of image processes, but then also give us a chance to interact with it in a more direct way, so we're able to kind of put in flags to only process a child or only process a parent, and kind of do additional checks rather than having it over in the image service and having to work with it a little bit in a different way. I would also say that another challenge has been the variety of rights and restrictions, and then also various kind of metadata fields that are wanted. This is mainly for that dam consolidation workflow. Since it's a new process, there's still quite a bit that's being figured out, and so it's kind of a constant negotiation of what metadata do we want to include? Do we need shot numbers for certain collections if we're expecting archivists to do their research in this new service? And as we're updating rights language with the legal team and leadership at the GRI, how are we incorporating that as soon as possible and making sure everything is accurate? How are we ensuring that downloads are possible when they're needed, but then restricted when they're not? Things like that. And so just a kind of quick thing is, how did we get here? And why do we have kind of all those different workflows, and how did we decide to kind of start implementing these new processes, updating our older workflows? And a lot of that is that version 3 was a really good excuse for us to kind of take a look at what we had done in the past and say, how can we make it better, and how can we make sure that we're compliant to the spec? I think generally we have the same end goal. We want to have linked art resources at the item level for everything, so HMOs, visual items, and then the manifests are extremely important to rendering the front end, which Dan and Sebastian will talk about. Another thing that was happening was the sunsetting of the Getty Search Gateway, and so that also really motivated us to focus on downloads and things that had different rights restrictions than our initial pilot project had. And then, yeah, I think a big overall thing that has been happening at the Getty is, yes, this item level metadata for archival collections. And I think we see that with Ruche, and I think JPCA collaboration that David and Andrew talked about achieves a similar goal and was really an inspiration for us to move the rest of our archival collections into kind of the same approach. Yeah, and I'll hand it off.
Hello. So that's all that's happening on our back end to generate all the data that we can then get on the front end for these two, with kind of the third application being JPCA, which is in a certain way kind of a reskinning of our research collections viewer, so it has a lot of the same logic inside of it. But these are both available on getty.edu at art/collection and research/collections, supporting all the visual items that we have either within our museum collection or that exist within our many archives and research items. And so just to give a sense of how these tools are built out, they both, well, all three of them use shared component libraries that are built within Vue.js, and you see I include in there, or Pinya, because we use Pinya for our store actually within our applications, which allows us, once we pull in all of this data from our backend, to then hold on to it as it's relevant to display and the individual logic that we use inside the application. That backend within our front end, our search server is built in Flask on top of Python, which that handles the relationship with Elasticsearch, which we use for accessing all of these JSON LDs inside of there, which we then bring in and then get indexed appropriately as we need them within the application. And I included on the far right side, this is kind of just like one of our directories of all of our helpers that we have. There are so many helpers that really make it pretty extensible to be able to support all the new data that comes in inside of as new information gets processed from our curators. And it's just showing you that we have a long list inside there that is always changing. And I think kind of the collection of all these things together allows for us on the front end to remain pretty flexible and take in new changes regularly, as well as, I think kind of as we alluded before, not have to think a whole lot about where this data is coming from on our source systems, as this is able to just kind of take in those final JSON LDs in our IIIF manifest and be able to render them out appropriately inside of our applications on the front end, particularly including our image viewer, which I'll toss over to Dan.
All right, so let's talk a minute about sort of where all of this ends up. The Getty image viewer is an internally built, developed, maintained IIIF image viewer that we use across all of our applications. Foundationally, it's built on top of Digirati's Canvas panel library, shout out Stephen, and the IIIF Vault library. So the message there is shared tools are wonderful, and you can build incredible things with them. There are a couple goals and premises that we sort of keep front of mind when we're working with the image viewer. We want it to be manifest first, or maybe presentation API first is probably the better way to say this. That is to say that all of the resources that Elena's team are generating, particularly manifest, we should be able to drop any manifest for any Getty object into that image viewer and get a sense of what it looks like, what you can do with it, and present something to the user that reflects the nature of the content that we're showing you, and the nature of the object that it represents. So whether that be an archival object, whether that be a paginated book, whether that be photographs of a museum object. We also are very focused on, in developing the image viewer, of building out and maintaining clear patterns for user interactions and rights information. We have a wonderful UX team who spend a lot of time thinking about these things. And again, similarly, as we use this image viewer across all of our applications, we want those patterns to be consistent so that users who are interacting with those pages know what to expect. And finally, maybe the most important thing that I've already kind of alluded to is we want to use this image viewer everywhere that we possibly can. what you're looking at here are 4 different instances in which we're using the exact same image viewer. One up there, the archival collections, Getty archival collections in our research collections viewer, a paginated book, a manuscript from the museum collection, a painting from the museum collection, and then finally down in the corner there, something from the Johnson Publishing Company archive, which David and Andrew talked about yesterday. This was our plan effectively all along. We, at one point, if we had given this presentation maybe 3 or 4 years ago, this would be 3 different image viewers probably. So we're really proud of this work, and we're hoping to extend it even further. Some benefits to the approach that we've taken here. We have effectively decoupled the data processing end of things from the display logic. I will reiterate, we don't, as a front-end developer team, we don't necessarily know or care what the source system of record for the data that we're presenting is. The presentation API effectively normalizes it and acts as a barrier so that we don't have to concern ourselves with that. This is an extensible model. As we build out new applications that have needs to present images, we will be able to rinse and repeat, modify the image viewer if necessary, put it into a new application. And finally, what this means for us is that upgrading API versions is minimally disruptive. Within the last few months, we have upgraded all of our IIIF resources from version 2 to version 3. For something that touched hundreds of thousands of resources, you would not know it based on the amount of effort that it took to do this. And so finally, I'll wrap us up with a little bit about what's next. Elena, do you want to come up here and talk about the migration?
Yes, so related to that DAM consolidation workflow that I mentioned, we are continuing to migrate those archival collections into RCV with different rights statements that we haven't dealt with before and new metadata requirements. This will result in lots of new IIIF manifests for various interesting archival collections like Schulman and Knoedler. There will eventually be a 4th approach that we will build out as new imaging workflows are being built at the Getty, and hopefully that will replace the other 2. Our hope is to be able to migrate everything over into our DAM system and into Arches, and then be able to build out a completely new workflow where we don't need to be worrying about moving things in between preservation systems and digital asset management systems. And then also we are beginning to look at advanced imaging formats, 360, 3D, scientific imaging, things like that. We're just starting to kind of play around with them, but I am sure the new version of IIIF will play a big part in that, and we're excited to kind of start taking a look.
And finally, one last note. This will probably be the last time that we talk about this and refer to it as the Getty image viewer. If you were here for the Johnson Publishing Company archive presentation yesterday, you probably heard about there's audio coming, there's video coming, there are complex objects that have interactive elements to them in terms of pages and turning. And so we are officially kind of transitioning from an image viewer to what we consider a digital object viewer, or the DOVE, so to speak. All right, thank you, everyone. We're here if you have questions.
I'm Tom Crane from Digirati, and I'm going to show you some really boring METS files. I'm going to go back in time many years. Now, this is work we're doing at Leeds, the University of Leeds, on digital preservation, but also kind of realizing that we can take advantage of tooling that uses IIIF even when we're not in a IIIF environment. So I'm just going to show you something first, and then I'll kind of go into more detail about what I'm doing. So this is the kind of digital preservation backend. Here I am preserving an extremely simple object, just some images, some snapshots, no real structure. So I'm just going to expose it as IIIF way before it becomes public IIIF. I want to expose the kind of working area, the deposit that I'm building up as IIIF. I can take it into a IIIF environment. There's a very kind of low-powered image server helping me do this. So I can see, there's my cats, I can see what I'm working on in a IIIF environment and think about how I might want it to appear as IIIF, even though at the moment it's just stuff in a deposit in our preservation system. I can use the fact that the manifest editor has a range editor to create structure. Because in my METS editing environment, my digital preservation environment, I might not have something to build a table of contents, or I might not like the piece of user interface that builds my table of contents there. I want to use a nice, shiny IIIF range editor, so I can do that. I'm just creating some structures, cats, maps, and other. This maybe is not a very realistic example, but I'm able to use a IIIF-based tool, and then I'm able, once I've decided that that's a good thing, I can use the manifest editor's ability to push the manifest somewhere so it gets saved and accepted back in the preservation building environment. So if I now wait for that to save and then I shouldn't be looking at this really. If I refresh this view, suddenly I've acquired a new logical structure here. I've acquired a table of contents in my preservation environment where this doesn't know anything about IIIF, but I was able to use an external IIIF tool to do this. And in fact, this is old school, storing everything in a METS file. This METS file has suddenly acquired a logical struct map that was essentially edited in a IIIF tool. And this is the idea here, that I can kind of use the growing libraries of fantastic IIIF tools to do work in a non-IIIF environment. I'm effectively making non-interoperable IIIF. Now, we said, well, why are you using METS files anyway? That's just like really old and uncool. And the idea, we did sort of tinker with the idea that maybe we could store a IIIF manifest itself as the kind of representation of the digital object in preservation. But then we thought, well, if you'd done that kind of years ago, you might be stuck with like a really old IIIF manifest. It's kind of actually quite a good idea to have a distinct standard for describing the structure that you can hang lots of stuff off. So as part of this work, we considered whether we should use METS. And then we decided, well, let's not reinvent that wheel. It's really well established. It's a standard way of modeling digital objects in the preservation world. It avoids us kind of latching onto any particular IIIF version. And also, the key thing here is that although we're kind of building METS in an old school way, we've now got decade or more of experience of turning those kind of representations into IIIF. And we know now, it's kind of pretty well established now, that IIIF is our target digital object format for the web. So we can make much more considered choices about how we construct METS with an eye to it becoming IIIF. So that's what this kind of things is about. Going to be about. Our kind of mappings that we're thinking about when we're creating stuff in a METS file, the physical arrangement is probably going to become canvases. The logical arrangement or arrangements, there's a mistake there, are probably going to become ranges, tables of contents, logical structure. We might want to record the fact that, say, well, this file is a transcript of that file. It's all saved in preservation, but when it comes to be turned into a IIIF manifest, one file might want to be an annotation on another file. We usually steer clear of using any descriptive metadata that got into a METS file because that's likely to be stale, but we are interested in using the relationships between structure in a METS file and catalog records, especially in archival hierarchies, because a single METS file might describe many items or pieces. And then obviously various metadata for access conditions and write statements. These are all things that we can think about how we want to model them in METS to make it easy to transform into IIIF. This is an example of a collection at the University of Leeds called Women of Westminster. It's a series of interviews conducted by the current Chancellor of the Exchequer, Rachel Reeves, with various female MPs. It's a single collection with multiple items, and each item is an interview that comprises, say, typically a recording and a transcript of the recording. As a kind of digital preservation task, let's make this thing. I'm not going to make the whole thing because that would be here for hours. But as a preservation task, the thing has been accessioned. It's likely a single preserved object because there's no, it's not going to change. So in the preservation kind of context, I'm making a single preserved object to which, again, you wouldn't probably do this manually. This process is more for kind of ad hoc stuff. But here I'm doing it manually. I'm just adding these files. I'm not going to, you'll see this jump ahead, so we don't have to go through this boring process. But I'm just adding some interviews and their transcripts to my object to be preserved. And that gives me a kind of a set of files, physical structure, Nothing strange going on here. I've just got the files so far. But if I wanted to think about, well, how would I want this represented in IIIF? Well, I can begin to think, well, okay, well, let's just associate this object with the collection level record identifier, give it an access condition and a copyright statement. So let's say this is leads MS2249. It's open and it's all in copyright. But now I can think about how in a IIIF manifest I might want to evaluate at an individual file level what kind of rights and access are being inherited. This redacted the unredacted interview with Angela Rayner here is going to be restricted. Maybe it has a lot of swearing in it, I don't know. But here you can see the effects of inheritance of access restrictions, because at the IIIF level, it's atomic on individual files rather than kind of inherited from a structure. So I need to know what the kind of resolved access condition is. Let's do a bit more work on it. Let's assert the relationship between documents. Here, I'm deliberately using presentation 4 vocabulary in a METS file. These terms, transcript, are taken from the presentation 4 API, the new provides property, which tells you, for accessibility purposes and other purposes, what one file provides to another file. So you can see here that they are now linked together. And maybe the redacted audio, which is the one that's going to be made public, has a link to it. It's a tidied up transcript. Again, I'm establishing the links between files with an eye on how they can be represented as IIIF later. And because this preservation environment, actually, let's just have a look at how that works in the METS file first. So there were my record identifiers that I added and connected. And there's the overriding record identifier, sorry, this second one here, the restricted access condition that's being applied. But those two links between the files, this is right down at the bottom, but these use the METS SM link element and use this role attribute with a URI borrowed from IIIF vocabulary, because it's going to become IIIF. Might as well use this vocabulary right here because it's totally fit for purpose. Do a bit more work on this thing with an eye to it becoming IIIF. At the moment, it's just one object, but the archival representation is a collection. So let's start doing some range editing. This time, not in a manifest editor, because it's pretty simple. I just want to associate these files with logical ranges. So I'm going to create a new logical section. Let's not call it a range. It'll become a range. A logical section. Now I've got some structure going on, and now I can associate parts of the logical structure with their individual archival records. So this one is MS2249/1, and the other one will be MS2249/2. So I'm just thinking about the future IIIF-ness of this, because this information might be used to turn this thing into a IIIF collection of IIIF manifests, one for each thing, rather than a single manifest. You can see there we're kind of inheriting the membership of a logical unit from the logical structure. So now we've got a logical struct map in our METS file, this time made natively rather than in an external IIIF tool. Do a bit more work on here. The point is, I can now view this as IIIF because this preservation environment has this means of turning it into IIIF just instantaneously, temporarily, and using all its knowledge to say, well, you've said this about this and that about that. Therefore, this is a canvas on which there is a painting annotation, which is the audio. Because you made that assertion of the connection between the two files, this transcript is a supplementing annotation with the provides property of transcript. This isn't quite accurate because this is a presentation 3 manifest with a presentation 4 feature, but anyway. It's there to be used. Everyone should start using these accessibility features of presentation 4 as soon as possible. And here's our kind of flip-flopping between IIIF and METS. Here the logical structure is expressed as ranges. So that's all cool. It kind of means that because I can expose my working area in my preservation environment as a IIIF manifest. I can take it outside of that and do some work on it as a kind of ephemeral throwaway IIIF representation. And it means, so here's the tool that was demoed in the morning session. What if I like that range editor better than my range editor? Well, I can just use that one. That doesn't know anything about editing METS files, but I can use it because it's a IIIF editor. I can take advantage of its ability to create structure. So I could use whatever tools I like. So let's use some more IIIF tools. This is a very simple digital object. It's a kind of reference video from the Blender Foundation. But again, I can view this as IIIF, and we know immediately that it should be a painting annotation on a canvas, because I haven't said anything else about it. But this is kind of completely unstructured. It doesn't have any information about what's in that video. But what if I take it again? I take it into a IIIF viewer, because it's a manifest, and I can play it. And so this is in Theseus. It's a working manifest. There is some kind of smoke and mirrors going on here with transcoding that you didn't see, because it's unlikely my preservation format is a web-friendly MP4, but we'll gloss over that. Anyway, I'm going to take it into the range editor again. So I'm just going to supply that manifest to the range editor. And this time, the IIIF manifest editor knows that there is AV on this canvas, and it gives me, as well as the normal range editor, an AV range editing tool in the manifest editor, which might not be something that you have in your. I certainly don't have this in my preservation environment for editing METS files. I don't have anything like this, but IIIF tools do have things like this. So I can take it in here, and I can start creating chapters. I'll press play. I'm just, again, I'm not. These aren't the official chapters of this video. I'm just going to make some random chapters using the tool that's in the Digirati manifest editor for AV ranges, which are kind of time segments, and I can kind of use typical tools from that kind of environment, like mark in and mark out. Here I am. I've kind of finished most of the video by now. I've marked out the chapters, and I've done all that kind of stuff. So I'm kind of nearly ready to take this back into a METS editing environment. But again, like, this doesn't know anything about my digital preservation concerns. All I want in the digital preservation world is the kind of a logical struct map that points at parts of the video. It will eventually be turned into IIIF again, maybe using these IIIF kind of shortcuts. But this is all about tooling, this kind of interoperability of tooling. By kind of creating an ephemeral IIIF representation, I can use tooling that understands IIIF to edit things that aren't IIIF. So I've finished that now. I'm going to go and save it. If I bring it back into here, I now have a logical structure that has pointing repeatedly at the same file, but different segments of the same file. And in the METS file, I've got a logical struct map that says the same thing, but in METS vocabulary with these METS area elements and begin times and end times. So I kind of round tripping backwards and forwards between IIIF representation. And really this is purely about kind of, well, I don't want to, if the user need comes up to edit chapters in AV material in the preservation environment, well, why should I reinvent a tool when I've got a really great IIIF tool for doing that over here? So having this kind of round trip scenario allows me to take advantage of IIIF tools in non-IIIF contexts. And that's it.
Okay, thanks to all our speakers, and we do have a few minutes for questions. So again, Bob and Glenn will be running the mics, and our speakers can come up to the stand to answer any questions. So anyone have a start off?
Yeah, I have a few questions for Ruven. Thank you very much for the benchmarking. Is the benchmarking suite available anywhere so we can run it against our own implementation on GitHub or something?
I did it all very simply using curl and bash loops,
Okay.
right? So I could, I mean, I think it would be useful for the community to have a standardized benchmarking suite to do this. And as it's run, in my case, I ran everything on bare metal, so you'd need to recompile everything for your installation. But no, so there isn't. I mean, it's just bash loops really. But I can. But it would be useful to have a standardized way of doing this. Yeah.
And I have another question for you about the virtualization overhead for Docker. That was kind of surprising to me, since Docker isn't really a virtualization technology, right? Did you run it on Linux or Windows, your benchmark with Docker?
Linux.
Okay.
So I was surprised as well by the scale of that. I mean, there should be some overhead, but what I found was actually more than expected. Yeah.
Did you profile it somehow, like a flame graph of where the time is spent?
No.
Okay.
No.
Thank you. And one last question about the hardware encoding. You mentioned CUDA and SIMD. Did you also take a look at like these media blocks in modern CPUs, like Intel QuickSync or the media blocks in SoCs, like for JPEG encoding or transcoding?
All right. No, not yet.
Yeah.
No, there's kind of more preliminary tests and things. The Intel One API implementation actually kind of works for IIP image, so I'm going to push that to GitHub soon. But no, I haven't tried. There's actually lots of, as you say, lots of interesting options available. So,
thank you.
Sorry, this was really not a question for Ruven, but something he may be interested in. The Kakadu software now actually has some GPU HTJ2K beta formats, which we'll get across to you at some stage. So you can actually compare those, which I think you'll find to be extreme acceleration, along with obviously we have an FPGA encoder now as well. So it's quite exciting for the HTJ2K world. Thank you.
This is for Tom. Just that I'm fascinated in this sort of METS to IIIF conversion process. And wondering if you have any documentation or references anywhere of those transformation scripts that you're using back and forth.
I haven't documented. It's all quite kind of on the fly at the moment. It is on GitHub, but I could do with kind of actually describing the process of doing it in a bit more detail than just code.
We would be fascinated.
But it's in a public repository, so I can send it to you. But it's nowhere near the main branch yet, because there are various smoke and mirrors going on with some of that. I mean, how am I? There's a little image, a mini image server running to do the images, and like I could only use video that didn't require any kind of transcoding, so it's all a bit. But the actual kind of conversion process. I mean, so obviously, as well as being able to have a IIIF representation to do that kind of tooling and go backwards and forwards, understand IIIF, turn it back into METS, understand METS, turn it to IIIF. It's then there's like a kind of, well, when I do come to make it into IIIF objects, I can apply the same, I can get the same view of it, and I'm kind of 90% of the way there already. But yeah, I'll send you some links.
Appreciate it.
I have a question for the first two presenters. Did you also benchmark or check cloud-hosted or commercial IIIF servers?
No, my benchmarks were limited to servers which are open source and that you can run locally. So no, I deliberately excluded cloud, because then it's difficult to compare their environment to hardware environment. So
Yeah, mine were all self-hosted options as well. Yeah.
Hi, I have a question for the Getty team. So, for example, for 12 Sunsets platform, so each photograph is a manifest. Have you thought of having also as a collection, right? Because you said that item level is like the most important thing that you want to get.
Yes, so actually as part of the initial implementation of the manifest process, there are collection manifests as well as manifests at the IE level. We kind of have turned away from that a little bit, as they're not really utilized by the front end. So a lot of the focus has been moved to that item level since it powers the front end more, but they do exist within our database.
Thank you. And a follow-up question, because in archives, most of the times when you don't have item level, so how do you do it? Do you populate you go one hierarchy level higher to get the metadata? So how do you cope with that?
Yes, so for the most part, when there's not item level metadata, we're going up to that intellectual entity level and using the descriptions from there, as well as some other metadata. Working like closely with the archival team, we can kind of get more down into the item level when it comes to things like rights restrictions. That's where it's kind of getting more specific to the item. But in terms of that more general metadata, a lot of that is at the intellectual entity level if we don't have it.
Thank you.
Hi. Another question for the Getty team. It's actually very nice to hear like the teams working together, because the majority of presenters here are just talking about one project. So thinking about we're releasing the 4.0, I'm just wondering, like, which part are you gonna like update first, and what methodologies you guys gonna choose? Like, is that the user? Is that organizational? Is that tech? Like, how are you gonna make a decision? Because you guys have so many moving parts. Thank you.
So first of all, thank you. Yes, we do have many moving parts. I would say when we are considering these types of decisions, and we just sort of went through this, migrating from version 2 resources to version 3, we often start by reflecting on sort of the very differences that Elena talked about, and sort of what is logical to do first. But we always sort of move from a data layer forward to a front-end implementation when we're doing these kinds of things. And so I'd imagine moving to version 4, that is what we will do first.
Another benchmarking question, I'm afraid. Do you have any sort of figures on the benefits of HTTP2 over 1.1?
Or even HTTP3. So yeah, this is definitely, when you're doing pan and zoom streaming, you have a sequence of tiles backwards and forwards. So there's definitely an improvement, especially with HTTP3. Yeah. In the benchmarks, I stripped out everything to do with networking, so I didn't measure that, but there is definitely, it's definitely worthwhile upgrading to HTTP3.
We have time for one more, if there is one more.
Also for